So we've said with TCP that one feature that TCP implements is congestion control. To see how that works, we need to first explain what causes congestion in the internet. Congestion occurs when the number of packets coming into our network exceeds the capacity of that network. The questions that arise then is, well, what is the capacity of some network? It's not easy to determine. There's no easy way to calculate the capacity of some network. The same as asking, what's the capacity of Bangkok's road network? How many cars per second or per minute can pass through all the roads in Bangkok? Then it depends on many different factors, the connectivity between the roads and so on, the number of lanes, the traffic lights and so on. And of course, same with the Bangkok road networks, what input sending rate, how many cars do we have to send onto the roads that causes congestion, traffic jams? Same with the network. How many packets per second do we need to send into the network to cause congestion? And then what happens when we approach that capacity? How does the network become congested, and how does that impact on our protocols? So we want to keep the number of packets we send into the network below some level which has a significant impact on performance. That is, you're seeing with your tests, your iPerf tests, you send at a small data rate, 1 megabit per second. Throughput is 1 megabit per second. You increase the data rate to 2. Throughput is 2. You keep increasing the data rate until you reach the maximum throughput, where increasing the sending rate is not going to impact upon throughput. So as we approach that capacity, in your wireless link, what happens? If I'm sending at some of you would have experienced it already. If I'm sending at a rate of 1 megabit per second, you'll see that you most likely get a throughput of 1 megabit per second. You increase to 5, and you may get a throughput of 5. 10, maybe you increase to 12, and you get a throughput of 12 megabits per second. Maybe you increase to 15, and you get a throughput of 12 megabits per second. And 20, it remains at 12. This indicates our maximum throughput, the capacity of our link in this case. What happens as we start to approach that capacity? Well, in this case, because we have a single link only, once we approach the capacity, we still get the same throughput. Once we exceed the capacity, we get the same throughput, but packets start to be dropped. That is the difference between the sending rate and the throughput would be the drop rate in that case. Now extend that concept to a network where we have more than just one link. We have a multitude of links all connected together. We have some capacity of the network, some maximum. As we increase our sending rate until we start to approach that capacity, what happens then? And it turns out that usually before we reach that capacity, we'll start to see significant performance degradation. The performance drops. And we said that if we have congestion, packets start to be delayed at routers. And for TCP, that may mean either the routers drop the packets. A router has a fixed buffer. If that buffer becomes full and another packet arrives, some packet's going to be dropped. It's not going to get to the destination. TCP will therefore have to retransmit. If TCP retransmits packets, then it's more packets it's sending. and causes more congestion. And as a result, more packets can be lost and more retransmissions. And if we keep going, eventually everything will be retransmissions and no original data will get delivered to the destination. That's why we need congestion control in TCP. We're going to look at 2 or 3 scenarios that illustrate congestion happening on a link between, or a set of links between hosts and destination, between source hosts and destination hosts via a router. This is just some illustration of typical performance to demonstrate how the congestion impacts upon throughput and delay. In this first scenario, we have host A sending to host D, shown by the blue line here. So the host A generates data, sends it onto this link to the router. The router is going to forward it to host D. And similar, host B is sending to host C. The sending rate is lambda in. That is a parameter that's the original amount of data that the host A generates. That's per host. And they both send, host A and B send onto this shared link to the router. And this link out of the router has capacity of R, the output capacity. So that's going to be our limitation. So coming into the router, what have we got? What's the rate at which data arrives at the router? What's the rate at which the data arrives at our router? We've got 2 hosts, A and B, sending. How would you write an equation or a formula for the rate of the arrival, of data arrival? Anyone? What do you think? No, you're thinking too much. It's very simple. Host A and host B are sending to the router. We've only got 2 source hosts, A and B, are sending across this shared link here. Let's say this is an Ethernet LAN. Maybe there's a switch here. So the host sends to the switch, and host A sends to the switch, B sends to the switch sends both of their traffic to the router. What is the rate at which data arrives at the router? The rate at which host A sends is lambda in. The rate at which host B sends is also lambda in. So it's 2 times lambda in. That's the rate at which data arrives at the router. A to D. Let's look at what host A sending its data to host D. Host A is sending at a rate lambda in. Let's say both hosts are equal, A and B, they get the same share of the bandwidth. What's the maximum throughput host A can achieve? Ignoring congestion, what's the maximum that we could achieve with host A? The best we can ever hope for? What's the maximum we can achieve with host A? Let's give some numbers so you can visualize this a bit differently. Let's say our sending rate, for example, is 1 megabit per second. R is 10 megabits per second. So host A is sending at 1 megabit per second. What is the throughput for host A? Host A is sending at 1. What's the throughput? What do you think? Host A is sending at 1 megabit per second. The router can send out at 10 megabits per second. There are two hosts sending, A and B. A is sending at 1, B is sending at 1. What do you think the throughput is for host A? 1. That's the sending rate, lambda in. The throughput, lambda out, is 1 megabit per second. We're never going to have a throughput that exceeds the sending rate. Okay. If we change that to, instead of 1 megabit per second sending, what if it was sending rate at 10 megabits per second? What's the throughput that host A can achieve? Host A is now sending at 10. Host B is sending at 10. Router output capacity is 10. What is the throughput at which an individual host can achieve? 5. We're limited by the router output capacity here. If each host is sending at 10, the total coming in is 20. We cannot get out at a rate more than 10 megabits per second. That's what this diagram illustrates. The throughput, lambda out, against the sending rate, lambda in. When the sending rate is less than R on 2, because we have two hosts, we're sharing this R capacity here between two hosts. So if we look at an individual host, just one, as if the sending rate is less than half R, R on 2, then we'll get that throughput. If our sending rate was 1, we'd get a throughput of 1. If our sending rate was 2, we'd get a throughput of 2. If our sending rate is 5, we'd get a throughput of 5. If our sending rate was 6, we get a throughput of 5 still. That is at this point here. Once we send at a rate greater than half of the output capacity of the router, our throughput is not going to increase. It's going to be fixed there. That's all that diagram is showing. We cannot exceed this capacity. That's perfect. That's what we'd expect. We know we cannot exceed this rate. We must divide it or share it amongst the number of hosts using that output capacity link, or output link. So that's okay with throughput. Now when we talk about the sending rate, in real life, the hosts are not sending necessarily at the same time, and they may not be sending at a constant sending rate. Their sending rate may vary. And we can think it varies in some random manner. That is, at some point in time, host A may have a lot of packets to send. Over a period of 1 millisecond, it needs to send many packets, and host B only has to send 1 packet. It depends upon the applications here. The sending rate on average may be lambda in, but at one instant it may be low, and another instant it may be greater than lambda in. But on average, over a long period of time, it's lambda in. So we may think that we have random arrivals of packets here. Sometimes host A is sending a lot, sometimes host B, sometimes both of them are sending a lot. On average, each host is sending at lambda in. The second plot here shows us, as we increase the sending rate, what happens to the delay, where the delay is really to do with the buffering delay at the router. Packets come in, we have some buffer at the router. And in this case, we're assuming it's an infinite size buffer, so we will never fill it up. As packets come in, they are stored in the buffer and then sent out. When the sending rate is small, say they're both sending at 1 megabit per second, means the amount coming in is 2 megabits per second. The amount that goes out is 10 megabits per second. The time packets spend in the buffer is going to be very small, almost zero. Because packet comes in, put in the buffer, immediately sent out, because we've got enough capacity on the output. But because they're sending at random rates, sometimes host A may send a lot of packets in a short period of time, and host B as well. They may exceed this sending rate. This is the average sending rate. If we draw a plot over time of the sending rate, if this is the average of 1, then the sending rate may be like this. Sometimes they're sending less than 1 megabit per second, sometimes slightly more. That may be for host A, and for host B, it may be different. Sometimes both of them will be sending at greater than 1 megabit per second, so the amount coming in will be greater than 2. If it starts to get close to 10, then we'll start to get some delay in the buffer here. But when we've got a small sending rate compared to the output throughput, our delay is quite small here. We increase the sending rate. As we increase the sending rate, there's a more chance that we're going to have to buffer some packets. That is, we may have a packet, 2 packets from host A, and a packet from host B in there. And since we have 3 packets in there, in the buffer, these 2 are going to have to be delayed for some time before they're sent. Because this one is sent, and then this one, and then this one. So as we increase this sending rate, our delay starts to increase. As our sending rate approaches this R on 2, where we get the flat throughput, in theory the delay starts to tend to infinity. That is, all the packets are coming in, keep filling up or being put in the buffer. We have an infinite size buffer, so the more we send, the more packets are going to be stored in the buffer and the more the delay is going to be. And if we increase the sending rate to infinity, our delay will increase to infinity.
The buffer will be used only the sending that exceeds the capacity of the router.
Only when the instantaneous sending rate exceeds the output link capacity. The rates that we're giving here are the average over time. So if this is time, and this axis is the sending rate, the flat line may be the average over time, but the instantaneous may vary. Because that's what happens in practice. Your computer is not sending all the time at the same speed. Sometimes it's sending a lot, sometimes it's sending very little. So it goes up and down. So even if the average sending rate is less than R, we still may get cases where the instantaneous sending rate is greater than R, and that will cause some buffering delay in that case. So as we approach this R on 2, our output capacity, our delay increases exponentially. And there's some theory behind this, that is some way to calculate why this is an exponential increase. So, in this simple scenario, our throughput is good. It's what we'd expect. Our throughput is the same as the sending rate until we reach the capacity, at which point our throughput matches capacity. Because we have 2 hosts here, each host gets half of the capacity, but if you combine the 2 hosts together, then they utilise the full capacity. So throughput is good, but delay is bad. because as we increase our sending rate, our delay all of a sudden goes very high. And when delay goes high, what happens? What happens with TCP if I send a packet and the delay for my packet to get to the destination is infinite? What's going to happen? Or infinite, it's very large, it's 10 seconds. What's going to happen? TCP, I send a packet, I'm waiting for an ACK, the delay for that data packet to get there is very, very large. What's going to happen? I'll retransmit eventually because I'll time out. I send my data, I'm waiting for an ACK. The data hasn't been lost, it's just been delayed a lot in the buffer. I'm waiting for an ACK, I don't receive an ACK, and therefore I'll retransmit, even if the data is not lost. So large delay can lead to retransmissions. Retransmissions means we're sending more into the network, which will increase delay even further. This is under the assumption that the buffer size is infinite. That's not true, of course. In this case, we extend using the same scenario, but assume we have a finite buffer size at the router. It's got a fixed size. Once it's full of packets and another packet arrives, let's assume that last packet that arrives is dropped because we've got nowhere to store it. There's no more space in memory. Now that's more practical now. The buffer has a fixed amount of memory. Once that memory is full, anything that arrives, either something needs to be dropped from inside the memory or the packet that arrives needs to be dropped. In any case, packets will be lost with a fixed size buffer. If packets are going to be lost, then that means our source will have to retransmit. So in this scenario, we denote lambda in as the original data, the sending rate of the original data. Lambda in prime, up here, is the original data plus retransmitted data. That's the total amount that's being sent by host A, lambda in prime. The original data, lambda in, plus all retransmissions. It's often referred to as the offered load. It's the amount the hosts are offering the network. They're loading the network with that traffic. If the buffer is full, which we'll get if our, go back. As we increase the sending rate, the buffer will start to fill up. Once it's full, new packets that arrive will be dropped and lost. The source will retransmit packets, leading to more packets being sent into the network. How does that perform? If we assume that we retransmit when we know that a packet is lost, if we say every second packet was lost at some point, for every original 2 packets sent, there'll be 1 retransmitted packet. That is, I transmit a new packet, and then I transmit another new packet. If every second one is lost, so the second one I transmit is lost, then for those 2 new ones I transmit, I'll need to retransmit 1 other packet. I'll need to retransmit 1 of them. In other words, for every 2 original packets sent, there'll be 1 retransmitted packet sent, or our offered load is 3 packets. And only 2 of them will be received. That's something you may be familiar with. We transmit some packet. It's received successfully. We get an ACK. We transmit another packet. It's lost. We so this is packet 1, this is packet 2. We retransmit eventually packet 2 and assume that's successful. Then over this period of time, we've sent 3 packets, this one twice, and we've received 2. Our throughput is 2/3 of our sending rate in this case. Therefore, as we send, as our offered load increases, we're not going to get the half of the R like we saw in this case. We're not going to get to the R on 2 here. Once we get to this sending rate, it's going to be less than that R on 2. In this example, R on 3. That is 2/3 of R on 2. 2/3, coming back to our example, R on 2 was 5 megabits per second. That was the maximum our host could achieve. In this example, if we get 2/3 of that, what do we get? Equals 2/3 of our capacity is 10 on 3. .33 megabits per second. That is 2/3 of this maximum value here. So the more retransmissions we have, the lower our throughput is going to be for the same sending rate. It can get even worse. This is under the assumption that I transmit a packet, I only retransmit when a packet is lost and I know that that packet is lost. But we've already said one thing that can happen, I transmit, I don't receive an ACK within time, I retransmit. In this case, a packet was lost. What about another case? Transmit, packet 1, successful. Transmit, packet 2. It takes a long time to get there. There's a large delay, a long time for the ACK to come back. I time out, and therefore I retransmit packet 2. In this case, because we have a large delay, we've retransmitted a packet. It wasn't lost. In the first case, this packet was lost. It dropped from the router. We retransmitted, which was the correct thing to do, and eventually got received. In this case, packet 2 is not lost. It eventually gets to the receiver, and an ACK will eventually come back. But since we have a timeout value, the delay for an ACK to come back was too long. So we retransmitted, thinking it was lost. We send that packet, and in fact, that may eventually come back as an ACK. This is bad as well. We've sent 1, 2, 3 packets sent. 1, 2 have been successfully received. This one's successfully received, but it's just a duplicate of this. We ignore here. So in effect, we've still only received 2 out of 3 packets sent in this case. And we've wasted, in this case, effectively, we've wasted a transmission. We didn't need to retransmit because the ACK eventually came back, but we did because we have a timeout value. And that degrades our performance as well. In summary, as we increase the sending rate of the offered load to the network, the throughput is limited depending upon how many packets are lost and how much delay is incurred on the packets. They were just very simple networks. We have 2 links, effectively. As you add more routers and look at a larger network, in general, the performance for throughput looks more like this. This is the amount we're sending into the network. This is the throughput. As we increase the sending rate, throughput's okay when we're at low levels. We're well below capacity. And we increase it, we get to some level before the capacity of the output link. And because we start to get packets delayed and eventually dropped, our throughput goes down. And our throughput can tend towards 0 in the end. Why 0? Imagine I'm sending a lot in, nothing's getting through, so I retransmit, and I keep retransmitting because none of my packets are getting delivered. They're getting lost, and therefore everything I send is just a retransmission of the first packet. No data is being delivered because everything gets to the router and is filling up the buffer and being dropped. So in general, we can think that the throughput heads towards 0, and that's bad. This is if we look at this more generally, this indicates that as our input sending rate approaches this point, we reach the maximum throughput, after which our throughput drops off. Therefore, we'd like to keep the sending rate below this level. If we reach this point and our throughput drops off, that's not good. So in congestion control, we'd like to keep the sending rate at a level such that we don't go over this hill here and performance degrades significantly. Knowing where that point is not easy. But in general, that's the objective. Keep the sending rate lower so that we don't have a large degradation of performance. We don't have congestion in that case. So in summary, how does congestion impact upon our network? We get large queuing delays. As the sending rate into the network approaches the output rate, the queuing delay goes up. That is, the delay packets are spent in the buffer in the queue increases. As the buffer fills up, some packets will be dropped from that buffer, and the sender must retransmit to compensate for those dropped packets. Every packet that's dropped, there'll be a retransmission. In some cases, there may be unneeded copies of packets sent. Like in this case. Here we had an unneeded retransmission. In theory, we could have waited longer and received the packet or received the ACK. But because we used a timeout, we retransmitted. That's a case of an unneeded retransmission. So these are bad things for our performance. We're sending too many packets into the network. And it can be even worse if we have multiple routers in a path. For example, we send some packet across our path. Packet 1 is sent to the first router, successful, and then across the second link, and then across this link, and then across this link, and then this one, the packet's dropped. Something goes wrong, or in this router, the router drops the packet because the router has its buffer full. We have a dropped packet, and it's being wasteful of all of these links because we're going to have to retransmit that packet across all those links again. So a packet dropped at one end of the path means that we've wasted the links or the capacity of the links across the start of the path. So we want to avoid congestion because it leads to poor performance in our network. How do we avoid congestion? Well, we implement a congestion control scheme, and there are two basic approaches for doing that. We can classify them as either end-to-end congestion control, normally implemented at the transport layer, which we're going to see what TCP does, and network-assisted congestion control, done at the network layer. In end-to-end congestion control, end-to-end, it's the end hosts that are performing congestion control. In this diagram, here's one end host, the source host, and the destination host. together, those two hosts follow some mechanisms such that they reduce congestion or control to avoid congestion. So it's implemented between the hosts, between the endpoints of the path. They don't rely upon the network. That is, they don't rely upon the routers in the network to give them any help in avoiding congestion. We'll see that's what TCP does, because TCP is an end-to-end transport protocol. It's implemented on the source host and the destination host, not by the routers. Network-assisted congestion control is when the network devices somehow assist in controlling congestion, the routers in this case. Here's an example. Here's our network. So we have a source host sending across a network of routers to a destination host. Two basic approaches. We want to slow down the sending rate if we experience congestion. Coming back quickly, this plot. Here's our sending rate, here's our throughput. We don't want to get to this point, because once our sending rate approaches here, our performance drops down. So if we see that we're approaching this point, we'd like to slow down, reduce our sending rate so that we back off a bit. So in network-assisted congestion control, we need to somehow tell the senders to slow down. And the senders may be the original host, but also the routers. Two ways we can get information. If the receiver detects that there's some congestion in the internet, then it could send direct feedback back to the source host and say, slow down your sending rate. So the receiver detects congestion through the assistance of the network, then the receiver, host B, sends some special message to host A saying slow down. How does it detect? The routers can detect congestion. This router starts to drop packets. Its buffer is full. Then it could send a special message onto host B saying the packets that are destined to you are starting to be dropped. That tells host B that there's some congestion in the network, and host B tells host A to slow down. So that's one approach, that the routers detect congestion because packets are dropped and inform the destination host, which then eventually informs the source host to slow down. Or the routers could directly tell the source host. This router detects in the buffer packets are being dropped, sends a special message back to host A saying, you're sending at a rate such that packets are being dropped in my buffer, therefore slow down. This approach involves the routers, and it means the routers must implement protocols to support this detection and notification. ATM, we've mentioned the technology before, uses network-assisted congestion control. It's one example technology. In the internet, and the basic internet, TCP implements congestion control, and therefore it's transport layered congestion control, end-to-end. So we're going to focus only on end-to-end congestion control from now on, transport layer, where the routers do not tell the hosts about any congestion and do not provide any notifications or measurements of congestion. It's just the source and end hosts that need to detect congestion and respond to that. And let's see how TCP implements that. How TCP works is the sending host limits its sending rate to avoid congestion in the network, or in the path. So it limits the sending rate such that it sends based on the perceived congestion it tries to get some measure of what it thinks is the congestion in the path and adjusts its sending rate based upon that. For that to work, the sender needs to limit the sending rate somehow. So we'll see that there's some algorithm for how does the sender limit its sending rate. That is, change the sending rate depending upon the congestion. Also, how does a sender know that there is congestion? How does it perceive network congestion? We have to see how that's implemented. And when there is congestion, how does it respond? And that's the TCP congestion control algorithm. There are in fact multiple algorithms. Some have been improved over time, and in some cases you can select different algorithms that have different trade-offs. Let's have a look at those three. How do we limit the sending rate? We need to go back to some basics of TCP. So the idea is that the sender controls its sending rate depending upon the amount of congestion. But how do we control the sending rate of a host? And we need to go back and understand how the sliding window mechanism works. For now, just ignoring congestion control, going back to the flow control mechanism to TCP. Sliding window flow control. We recall that there's some window of, or some size of the number of packets we're allowed to send before we have to wait for an ACK. Let's say W, the window size. What that means, we can send, if W equals 4, for example, we can transmit 4 packets, after which we cannot send any more until we receive an ACK. This is the basic concept of flow control. I send 4 packets. If my window is 4, it means after transmitting those 4, I'm not allowed to send any more until I receive an acknowledgement. When I receive an acknowledgement, it allows me to send more. Why? Because with flow control, there's a buffer at the receiver. The received data is put into the buffer. An acknowledgement from the receiver, or the acknowledgement number, indicates how much space is available in the buffer at the receiver. So as we receive more acknowledgements, in general, we can send more packets. I receive an acknowledgement, I can send another packet. Then eventually I'd receive this second acknowledgement, allowing me to send another packet. Not very accurate anymore. That's the basic concept of flow control. The receiver controls how fast the source can send based on the rate at which ACKs come back. In TCP, it's not just the ACKs, it's the window size in the TCP data frame. The TCP segment has a window field. When we send the TCP ACK, or the TCP segment back, we set the window field to be the value which indicates how much space is available in the buffer. If our buffer could hold 4 packets, or 4,000 bytes, and we have 3 packets, or 3,000 bytes in the buffer, then we could set the window to be 1,000, or 1 packet, saying I've got space for 1,000 bytes, and send that in the ACK. We send 1,000 bytes, and as the buffer space is increased, we can increase the window size that comes back. So the window value in the TCP segment that comes back indicates how much the source is allowed to send, But the basic approach is that it indicates we can send packets up to some maximum window, and then we can only send more packets when we're informed that that window is greater than 0. That is, we get the ACKs back. What's the maximum rate at which we can send in this case, approximately? For example, we have a window of 4. What does it depend upon? The maximum throughput. If we keep drawing this, if everything was perfect, we'd send a packet, we'd send 4 packets, we have to wait some time, we receive 4 ACKs back, allowing us to send those 4, then we wait some time, send another 4, and so on. We could send, in this period of time, 4 packets. So in this period of time here, we're sending 4 packets, and another 4 packets in the same period of time, and so on. And same at which is the same for the receiving rate or the throughput. We receive 4 packets, and then we receive nothing. Receive 4 packets, nothing. 4 packets, nothing. So our throughput is 4 packets per this period of time. What is this period of time? Well, how could we calculate or approximate that? Let's send another 4 packets. I'll draw it slightly different. I've tried to draw it, same 4 packets, but a longer period of time here. How would you calculate this period of time? Write an equation. Try and write an equation right now that calculates that period of time based on your knowledge of delay. Let's give it a value, x. X equals what? Based on your knowledge of transmission delay and propagation delay, what do you think is the equation for calculating the value of x? I've seen one solution. Anyone else got a solution, an equation? X equals, what about transmission delay? So people are on the right track. Let's calculate it, going back to the very basics. From here, the time at which we start transmitting the first packet until we receive the first ACK. You see, we transmit a packet. Let's call this, I'll call it uppercase T for transmission time of one packet. The time from here to here is T, or the transmission time. Transmission delay for one packet. And once we've transmitted that packet, it needs to propagate to the other side. So we have propagation delay. And then we transmit an ACK back. I haven't shown the ACK visually here. That is, I've assumed the ACK is very small. Often, but not always, often the acknowledgement maybe is very small compared to the data. So the larger the packet, the larger the transmission delay. We could say plus the transmission delay of the ACK, transmission of the ACK. But let's keep things simple and say that's approximately 0 compared to the other values. And then that also needs to propagate back. That is this time. So we also have processing delay here. And because this is a network, we may have queuing delay. Well, in fact, when I say propagation delay, that's just for a link. If it was a network, that is, there are routers here, it would be the propagation across the first link, processing and queuing in the first router, propagation and so on. We've simplified to just the time to transmit, the time the packet to propagate across the network or the link, plus the time to transmit the ACK. Well, let's make that 0 to make our equation simpler, plus the time for the ACK to propagate back. Which, so let's say, is the transmission time of our data packet plus 2 times the propagation time of a packet. Now, of course, when we talk about a link, we don't talk about propagation time. We normally talk about what? The time it takes for a packet to get from the source to the destination and back is round trip time. Most of you have learnt this in labs over the last week or so. A program called ping reports the round trip time, the time it takes a packet to get to the destination and come back. That's what's happening here. The time to get this packet to the destination and back is our round trip time, which is 2 times the propagation. So it's precisely transmission plus the round trip time. What about for the second packet and so on? Very similar. If 2 times the propagation is our round trip time, then in many cases the transmission is very small compared to the round trip time. If you remember when you use ping, if you used a ping with a packet of 56 bytes, you may get a transmission time, of a round trip time of 0.13 milliseconds or whatever it reports. If you increase the packet to 60 bytes from 56, then the value reported would not be much different. Increase it to 150 bytes. Across the internet, the major contributor is the round trip, is the path propagation, the queue delays at routers and so on. So we say in a network, this time is approximately the round trip time. That is, we can send W packets every round trip time. Round trip time, the time for a packet to get there and back. Because when when the ACK gets back, we can send more. In fact, another W packets. In our example, W equals 4. Approximately, our sending rate, we send W packets every round trip time. And that's also our throughput. We receive W packets every round trip time. Sending rate is approximately the window size divided by the round trip time. Not exactly, but if the round trip time is fixed especially, it's very close to that because of how our flow control works. That's flow control, that's not about congestion control. We said with congestion control, our aim is to control, one thing we want to do is control or limit the TCP sending rate. So how do we change the sending rate of our TCP source? Well, this gives us the hint. Our sending rate is approximately equal to the window size divided by the round trip time. How do I increase my sending rate? What am I going to do to increase my sending rate? What am I going to do to increase my sending rate? Increase the window size. Make window size larger, sending rate becomes larger. Want to decrease the sending rate? Decrease the window size. We cannot modify the round trip time because the round trip time is the time from our computer to go across the internet to the destination and back. The source has no control of the round trip time. That depends upon the network. So that's something that's outside of our control as the source. We can modify the window size at the source. So to control my sending rate, I will vary the window size. And that's how TCP sender controls its sending rate. Now coming back. With flow control, the window size is informed to the sender based upon the value set in the TCP segment set by the receiver. That is, the receiver sets the window to be some size depending upon the amount of space available in the buffer, sends it back in an ACK, and the sender then has the window of which it's allowed to send. We refer to that window as the advertised window. That is, the window used for flow control is the advertised window because it's advertised by the destination. The destination tells us how much we're allowed to send. That's for flow control. But we want to control the sending rate for congestion as well. TCP has another window. It now has two windows, two parameters, the congestion window. And we will change the congestion window depending upon when we sense or perceive congestion in the internet. If we think there's some congestion in the internet, I will decrease the congestion window so that I decrease my sending rate. If I think that there's no congestion in the internet, or at least on my path, I will increase the congestion window and allowing me to increase my sending rate. So for flow control, we have an advertised window, and for congestion control, we have the congestion window. The TCP source can send the amount of data it can send depends upon the minimum of those two values. If, for example, the destination has sent some segments back, the buffer space had a buffer, the space available at that point in time was 2,000 bytes, then we're in the TCP segment coming back, the window header field will be 2,000. So there's a field in the TCP header, the window field. That indicates the amount of space available at the receiver's buffer. That's for flow control. When the source receives that, the advertised window, AWND, equals 2,000. If we receive later some other, another TCP segment, when the buffer space has changed to 3,000, that is, there's more space available in the buffer, then the window size here would be 3,000, and this is an A. AWND, advertised window at the source would be set to 3,000. That's flow control. The destination is telling the source how much space is available in the buffer such that the source will not send too much to overflow the buffer. And that's maintained at the source in a variable we call the advertised window. In addition to that, for congestion control, we have a second variable, CWND. And we have a separate algorithm for updating that value. We're going to see in detail how that changes. But first, we'll see how the value changes shortly. The source has two variables, advertised window, congestion window. The amount that the source is allowed to send is the minimum of those two. So at this point in time, advertised window is 2,000, congestion window is 2,500. We're limited by the advertised window. It's the minimum. Sometime later, the advertised window increases. We may be limited by the congestion window. Simply the minimum of the two indicates how much we're allowed to send. That's here. The number of bytes we're allowed to have outstanding is the minimum of the advertised window and congestion window. We don't have to send that much, it's the maximum we're allowed to send. Until we have to wait for some more acts that allow us to send more. Advertised window controlled by the destination. How is the congestion window controlled? Well, we have a congestion window, a congestion control algorithm that modifies that variable. Our sending rate is still the window size, approximately the window size divided by round trip time, where the window, let's say, is the minimum of these two values, advertised and congestion window. For the rest of the explanation here, we want to focus just on congestion control and see how that works. So to do that, let's assume that the advertised window is very big, always larger than the congestion window. Let's say it's 200,000, doesn't matter. If advertised window is very big, that is the buffer at the receiver is very big, then the congestion window will always be the minimum. And our sending rate will depend upon the congestion window. Let's just assume for simplicity to explain how the congestion window works, assume that the advertised window is very large. That is, the sending rate is approximately equal to the congestion window size divided by the round trip time. Given that, we're going to adjust the congestion window depending upon how much congestion we perceive in the network. Before we move forward, let's make sure everyone's clear on how we've got here. Yep.
Do the various access point and the switch have buffer?
Do the wireless access point and switch have buffers? Yes, normally they do. When we draw our network, where can I draw it? If we think about internet path, we have a host, a router, some routers and destination, the source of the destination. Of course, these links may be made up of not just a single cable, it may be, in fact, a wireless link. You don't have to draw this one, an access point connected to a switch, connected to the router. They may have buffers as well. That is,
Can I say that all network interface must have buffer?
most network interfaces have a buffer. You don't have to. It just means that Well, what's a buffer? A buffer is just some memory that you store. You need at least enough memory to store one packet. If you generate a packet, or if you receive a packet, you need to be able to put that in memory as you process it and then send it out. In practice, most network devices, network equipment will have buffers so that they can receive 10 packets, process the first, send it out the second, and so on. Yes. Any other questions related to TCP? Yep.
The congestion window is controlled by the router?
No, the congestion window is, we'll see, we haven't seen it yet, but so this is the source host. So my PC, this is the destination host, a PC on the other side of the world. There's routers in between us. In TCP, it's an end-to-end congestion control scheme. The routers have no part in what's happening here. Routers just receive a packet, forward it on. If their buffer is full, they'll drop it. We'll see that the congestion window is controlled by an algorithm at the source. It will change the value according to some algorithm, depending upon different things that happen, which we're about to go through. So the routers have no role in the congestion control. Any other questions before we move on? Advertise window used for flow control, congestion window used for congestion control. We have both control mechanisms in play at once. But to look at how congestion control works, we're going to ignore flow control by saying that the advertised window is very large. How do I know that there's congestion in the internet? How do you know that there's congestion at some place in Bangkok when you want to drive to the centre of Bangkok? You finished your last class today, you want to go into the centre of Bangkok. How do you know if there's congestion on the roads? What do you do? Experience, okay, based on past measurements, yeah. Maybe you know that a particular intersection at that point in time is busy. You could, maybe in theory, you could send someone in front of you. Maybe your friend, say, go drive through and tell them to report back and tell you where the congestion is. That would be nice of them. But that's similar to experience based on someone who's been there before. If you could get particular reports from the intersections, maybe they send SMSs to you saying if there is congestion or not. How does TCP source know? How does this computer know that there's congestion in this internet without getting precise feedback from the routers? The congestion occurs at the routers. How does the source know that there's some congestion here, that is that some routers are dropping packets, without these routers explicitly telling the source? With transport layer congestion control, it's just the source and destination that are involved in this. So what does TCP do? It assumes a packet loss indicates congestion. I send packets. It's like you send, there's 20 of us that want to drive into the city, 20 separate cars. If the first one, and when the first one gets there, they call back and tell us that we've got there and the next one goes. If the first person doesn't get there, or takes a long time, then the second one knows that there's some congestion in the path. Here, we send our packets. If a packet doesn't get to the destination, it's lost, or the ACK doesn't come back, then we assume that that packet was dropped by a router due to congestion. So it's very simple in this case. TCP, the sender assumes any packet loss indicates increased congestion. The more packets lost, the larger we assume the congestion is. How does a TCP sender know the packet is lost? Two basic ways. Timeout occurs, or we receive 3 duplicate ACKs. If we again recall back to the retransmission scheme, there were 2 approaches in TCP. I send. If I don't receive an ACK within some timeout period, I assume a packet's lost. But there was another one called fast retransmit. I send multiple packets. If I receive 3 ACKs with the same ACK number, 3 duplicate ACKs, I assume a packet has been lost. So we have 2 different events that indicate a packet loss. Timeout or 3 duplicate ACKs. Is this the right thing to do? Well, in practice, in many networks and in the internet, most packet losses do occur at routers due to congestion. But in some particular cases, for example in wireless networks, some packet losses occur not due to congestion but due to other problems. For example, the link performance is not good. Here's our path. We send our packets through the network. This router is busy because it's not just carrying the traffic in this direction, there are others sending into this router. It has many links into it and it has a limited capacity going out. Many people are sending packets in, including our source. Its buffer is getting full. Eventually it drops our packet. From this source to this destination's perspective, we've sent a packet here. It gets dropped because the buffer is full. That is, congestion is occurring at this router. That packet is dropped. Eventually, our source will time out, or it will receive 3 duplicate ACKs. So some event will occur that indicates that the packet has been lost, and that's when it will change its congestion window to cope with this congestion. That works okay. What may cause problems sometimes is, here's our wireless LAN link. I have an access point, this is my laptop. There's no one sending into the routers. No congestion at the routers, buffers are empty, packets are going through very fast, everything's good in the rest of the path here. But our wireless link, for a small instant, is very poor. Someone walks between my laptop and their access point and I lose a packet. That is, the wireless LAN tries to retransmit, it's unsuccessful. Effectively, a packet that I've transmitted has not got to the destination. So if we lose a packet due to poor wireless link, not due to congestion, then again TCP will assume that this is due to congestion. Any packet loss that TCP recognises, it assumes it's because of congestion in the internet, and therefore it will slow down. But if the packet loss is due to some other reason, like our poor wireless link, TCP will still slow down, but that may not be a good response, because if it's a poor wireless link, you don't need to slow down. The reason TCP slows down is because it wants to avoid congestion. But this is a packet drop due to something other than congestion, and therefore we should not slow down. But still, in most cases, a packet loss in the internet is a good indicator of congestion occurring. Therefore, if we detect a packet loss, then we assume increased congestion. How do we know decreased congestion? If we receive ACKs. Receive an ACK means our packet wasn't lost. I send one packet, I receive an ACK for that, it wasn't lost. That means my data is getting through, so the more ACKs I receive, I will assume the less congestion there is in the network. The more packets that are lost, the more congestion in the network. Given that, we can then derive, or we can work out how define the congestion control algorithm. How does TCP respond by changing the congestion window value depending upon those different events? So let's make note of what we have so far. The sending rate we know is approximately equal to the window size divided by the round trip time. We can control the window, we cannot control the round trip time. It's a characteristic of the network. For this discussion, we're assuming the buffer at the receiver is large. If the buffer is large, very large, it means there will always be space in the buffer, and the advertised window will be large as well. So in other words, the advertised window, we're going to assume, it's not always true, but for this discussion, advertised window is always greater than the congestion window. Because our sending rate is the minimum of the two, then if this is advertised window is always greater than congestion window, the minimum will always be the congestion window. What else? TCP assumes if we have a packet loss that there's increased congestion in the network. And there are two types of packet loss, or two events that indicate a packet loss in TCP. I send a packet, I don't receive the ACK within a timeout. A loss due to a timeout. But there's another case that can occur. I send a packet, I've actually sent many packets, I receive 4 ACKs with the same ACK number. That is 3 duplicate ACKs. That's also a trigger for a packet loss and a retransmission. Two different events indicate packet loss. Packet loss, we assume increased congestion. An indicator of decreased congestion, that is everything going well, is that my packets get there to the destination and the ACKs get back. That is, I receive acknowledgements. As I receive acknowledgements, I'll assume that the congestion has gotten better. It's decreased. As I lose more packets, I will assume the congestion has increased. And my goal now is to control my sending rate depending upon these events. If I detect increased congestion, decrease my sending rate. And if I detect decreased congestion, increase my sending rate. And that's where we get the congestion control algorithm. So a summary of the things that we've arrived at so far. So now we have some algorithm at the sender that's going to change the value of CWND, the congestion window, depending upon these events, the loss and the reception of ACKs. Basically, congestion window goes down if these events occur, and this event, the congestion window goes up. That's the idea. Less congestion, the more we can send. The more congestion, we should send less to avoid congestion. Remember, we'd like to send data as fast as possible. Okay? So we want the congestion window to be as high as possible to get our throughput high. But we don't want to reach this sending rate that results in us getting to the top of the curve and our throughput dropping off quickly and our delay going up. We don't want to reach capacity, because once we reach that capacity, delay goes up, packets start to be dropped, throughput goes down. So control the sending rate so we're just below that capacity of the network. So TCP congestion control algorithm has a number of components. We'll go through in order. Additive increase and multiplicative decrease. That's the ways at which the basic ways in which it increases the window and decreases the window. In an additive manner, increases, and in a multiplicative manner, or an exponential manner, it decreases the window. We'll see that for certain cases, the slow start mechanism, not the slow tart, the slow start mechanism is needed at the start of a connection to improve performance of our connection. We'll go through that. And then we'll explain how the different loss events, we see we have two different loss events, how we react to them differently. So we'll go through additive increase, multiplicative decrease first. To explain how these work, we'll use different terminology. We'll mention the maximum segment size. We talk about TCP as a byte transfer service. We send bytes, we receive ACKs for those bytes. To keep things simple, we'll talk about segments or packets of some maximum size. If we have our network, the links may have different maximum size frames that they can send. Ethernet may support 1,500 bytes. This link may be 800 bytes. This link 1,000 bytes. That's the link layer technology have some limits on the maximum frame sizes supported. TCP will try to not send a frame larger than the minimum of these link maximum sizes. That is, in this case, it will try to set the maximum segment size to be no larger than 800 to avoid fragmentation. Because if we set it to 1,000, if we send a 1,000 byte TCP segment, it's okay across this link, but across this link we'd have to fragment that into 2 IP fragments, because this link only supports 800 bytes. So we'll assume we have some maximum segment size which is determined or assumed by TCP sender. It's the maximum size segment we can send across each of the links. Maximum transmission unit you'll see somewhere. I think it's the same except in terms of the headers. Maximum segment size takes into account the headers. That is, I shouldn't say 800. This is the size, for example, of the Ethernet data. So Ethernet, the data can be 1,500 bytes. What is the data? It's an IP packet. The IP header takes up some space, say 20 bytes. So in here is 1480. So if this is 1,480 bytes, what is this? This is our TCP segment. the maximum segment size is this value, the size of this. I think the MTU, maximum transmission unit, may be 1,500, whereas the MSS would be minus the IP header, minus 20 bytes. So almost the same, but differ in terms of how they include headers. But basically what they're doing is indicating what's the maximum size segment, packet or frame that we can send across a path to avoid fragmentation. Fragmentation is bad because it's complex and it leads to more overheads. So we have a maximum segment size. Let's assume we know it. All right, we've mentioned we've got a congestion window, CWND, measured in bytes. Maximum segment size measured in bytes. Sometimes we'll mention not in bytes, but in packets, or maximum, or in terms of segments. We'll see that shortly. And we have a round trip time, the time for sending a segment until we receive the ACK. And we'll assume that the receiver, every time it receives a data segment, it will send back an ACK. That is a TCP segment with the ACK flag set. It doesn't have to be that case, but for our examples, we assume that. Let's go through additive increase, multiplicative decrease. This is the basic way in which we decrease the congestion window and increase the congestion window depending upon the congestion. Additive increase. This is increasing the window in the result of decreased congestion. If there's no congestion detected, then the sender assumes we can send a bit more because we haven't approached the capacity. If we have some capacity, if we're sending at a speed which there's no congestion, then it means we're probably not near capacity yet. So let's send a little bit more and send a little bit more until we get close to capacity. And then congestion will start and then we may slow down. Because we don't want to approach capacity and go past the capacity for our sending rate, we only increase at a slow rate in an additive manner. The aim of the sender is to increase the congestion window by one maximum segment size every round trip time. Let's see how that works. For an example, let's say the maximum segment size is 1,000 bytes. And we have a round trip time which is fixed and it's 100 milliseconds. In reality, the round trip time is not fixed. It varies in the internet. But let's keep it fixed. Then the goal here is you don't have to draw this diagram. You'll see on the later slides we have something similar to this. Not the same, but just demonstrate the simple approach. Here we have time. We start transmitting data. We start with a congestion window of some initial value. we need to be able to send something. If the congestion window is 0, it means we can send 0 bytes and we'll never receive an ACK. So we start with some positive value for the congestion window. Let's say it's equal to 1 maximum segment size. So initially, we can send 1,000 bytes. We transmit 1,000 bytes. Let's draw that. At the start, I transmit 1,000 bytes and packet propagates, ACK comes back. After 1 round trip time, we want to increase the sending rate. So we increase the congestion window. In this case, our goal, it was at 1,000. After 1 round trip time, after 100 milliseconds, increase it up to 2,000. That is, increase it by 1 maximum segment size. Originally we could send 1,000, now we can send 1,000 plus another 1,000, 2,000. So that was 1,000 bytes sent. We receive an ACK. We're now allowed to send 2,000 bytes, which may be 2 segments. We transmit them. ACKs come back. So this is approximately 1 round trip time. Send 1,000. When we receive that ACK, increase our congestion window. It was, I'll write it over here, the congestion window initially was 1,000. When we receive the ACK, after 1 round trip time, we increase it to 2,000. Because in our example, MSS, the maximum segment size is 1,000, which means we can send 2 packets. The goal is that every round trip time, we increase by 1 maximum segment size. Start with 1,000 bytes. After a round trip time, after 100 milliseconds, increase to 2,000. After another 100, increase to 3,000, 4,000. This is the congestion window size. This is the time. Every round trip time increased by 1 MSS. That's our goal for slowly increasing our sending rate. Let's continue and see how it works here. We sent 1 because our initial value of the congestion window was 1,000. We get an ACK back. We send 2 segments because our maximum segment size is 1,000. We're allowed to send 2,000. So we send 2 segments. We get 2 ACKs back in approximately 1 round trip time. Okay, we send segment and get an ACK after 1 round trip time. The time at which we receive the second ACK will be a very short time after, because the transmission delay is usually very small compared to the rest of the delays. To make that clear, let's be precise. Let's give these numbers. Start transmitting at time 0. Let's say the transmission delay is 1 millisecond. The time for our packet to get to the destination on the other side of the internet and come back is 99 milliseconds. That's 99. So from here to here is 100. The round trip time is 100 milliseconds. So here's 100. We're now allowed to send 2 segments because our congestion window is now 2,000. We send 2. This takes 1, it brings us to 101 and 102. Only takes a small amount of time to transmit that segment. We receive the ACKs back. It takes 99 to get back, so this one is received at 200 and this at 201. Approximately, we've received the 2 ACKs after another round trip time. Okay, we've received 2 ACKs at time 201, but it's approximately at time 200 because the transmission time is very small in that case. We'll come back to that. We've sent 2,000 bytes. After the next round trip time, the goal, increase the congestion window by another maximum segment size, increase it from 2,000 up to 3,000. So now the window becomes 2,000 plus MSS equals 3,000. So after the first round trip time, the second round trip time, now we can send 3,000 bytes, or 3 segments. Running out of space. And my diagram is not very good because it's not to scale, it's nowhere near scale, but again, the transmission time of these packets is very small. 201, 202, 203, 204. Round trip time, time to propagate and come back, 99, so brings this to 301, 302, 303, but approximately 300. That is, we receive those ACKs all around the same time, give or take a few milliseconds. So this was one round trip time, this was the second and the third. And now we'd be able to send, we want to increase the window up to 4,000. And so on. The goal is this additive increase, or this linear increase in the window against the round trip time. Every round trip time increased by 1 maximum segment size. That's the goal with a congestion control algorithm. Because we're receiving ACKs, we assume that there's no congestion in the network. So I increase my sending speed, trying to probe whether there is more capacity in the network. I keep increasing slowly in a linear manner, with the goal of 1 MSS every round trip time. But we see it's not exactly every round trip time. If we did the calculations, we send 1 segment, receive 1 ACK in 100 milliseconds. We then send 2 segments, receive 2 ACKs in 101 milliseconds, approximately 1 round trip time. Then we'll send 3 segments, receive 3 ACKs in 102 milliseconds, which is approximately 1 round trip time. I've gone through this detail because how do we implement this process of every round trip time increment by 1 maximum segment size? This is one way to implement it using this equation here. Instead of every round trip time, every ACK you receive, you increment the window. Let's see. Our window started at 1,000, initial value. We received the first ACK, okay? The goal was to increase now to 2,000. So 1,000 plus 1,000 is what we want. Then we transmit 2 segments and we receive 2 ACKs, the first one and the second one. What we want is some equation that makes it simple to implement at the source, that every time we receive an ACK, we increment the window. This is one such an equation, where we increment by the maximum segment size squared divided by the old window size. Let's see how that works. Original value 1,000. Receive 1 ACK. Take the old value and increment by MSS squared divided by the old value. In our case, MSS, the maximum segment size is 1,000. So we take the old value, 1,000 bytes, plus 1,000 squared divided by 1,000, the old value, and we get 1,000 plus 1,000 equals 2,000. Which is equivalent to our goal. Our goal is to increase by 1 every round trip time. But now we're increasing every ACK received. There's a slight difference. Let's see how it works. We send 2 segments. We receive the first ACK. We apply our equation, running out of space. Separate this. Now we take the old value, which is 2,000, plus MSS squared, 1,000 squared, divided by 2,000 equals, who has a calculator? Ready for your exam next week? You have your calculator? Okay, I think I've answered somewhere. If not, I'll use my calculator. Let's quickly go through this before we finish. $1,000 squared divided by 2,000, 500. We're up to 1,000. Oh, that was an easy one. 1,500. Sorry. 1 million divided by 2,000 is 500. We're up to 2,500. But we quickly receive a second ACK. That was the calculation when we received the first ACK. Then immediately after we receive another ACK, we apply that equation again. It becomes 2,500 plus 1,000 squared over 2,500 equals 2,000. We've got 1,000 squared divided by 2,500 plus 2,500, 2,900. That is the congestion window size after receiving the second ACK here. 2,900 bytes. Almost the same as our goal of 3,000 bytes. Close enough. We wanted to increase to 3,000 bytes after the second round trip time. If we implement that algorithm of every ACK received increased by MSS squared divided by the old value, it approximates this. It's not the same, but it's approximately equal to 2,900. And you can follow through. What if we receive 3 ACKs? That is, apply this algorithm 3 times, see what you end up with. It will be close to 4,000 bytes. So that's a way in which the additive increase algorithm is implemented. The goal, every round trip time increased by 1 MSS. The implementation, every ACK increment by MSS squared divided by the old value. I suggest what you do is finish, at least do that for the next round trip time. That is, do the calculation for those 3 ACKs are received, see what you get for the congestion window. It should be, well, it's going to be slightly less than, but it's close to 4,000 bytes. We'll spend maybe 20 minutes or so tomorrow saying a little bit more about the TCP mechanisms. We won't finish TCP tomorrow because we want to have some time to discuss the exam. So just at the first 20 minutes we'll finish on TCP, and then tomorrow we'll discuss the exam and go through some practice questions. So